wondered what would happen if the geometry we know was different. What if a triangle's interior angles did not sum to exactly 180 degrees? What if through one point there were many parallel lines or even no parallel lines at all? So today, our group will explore how changing Euclid's assumptions, especially the parallel postulate, can create entirely new geometric worlds beyond the flat space we usually study.
What if one simple assumption could completely change the way we understand space and shapes? The Greek mathematician Euclid assumed that through a point not on a line, there is exactly one parallel line that can be drawn. This is known as the parallel postulate and is a basic rule in Euclidean geometry. What happens if it changes? If the assumption is changed, geometry also changes. For example, there could be no parallel lines or many parallel lines through a point. This leads to different types of geometry, like non-Euclidean geometry, where shapes and angles behave differently from what we usually expect.
Now, let's investigate triangles drawn in two different surfaces. On a flat surface, we draw triangles ABC, PQR, and XYZ. When we add up their interior angles, each triangle always has an angle sum of 180 degrees. But what happens in a curved surface? In a curved surface bowl, we notice something different. Triangle angle sums are not 180, but greater. Therefore, shape behavior and angle sum of triangles depends on the surface they are drawn.
What if geometry didn't follow the usual rules? This diagram shows the Poincare-Diss model of hyperbolic geometry, where everything exists inside a circle and the boundary represents infinity. You can approach it but never reach it. The lines may look curved, but they are actually straight paths called geodesics, or the shortest distance between points. In this space, parallel lines behave differently. Some never meet, some meet only at infinity, and others move away from each other completely. Even triangles are different. Their angles add up to less than 180 degrees. This shows that geometry depends on the space we are working in. What if
We found two important results during the activity. First, the sum of the angles in a triangle changes depending on the surface. On a flat surface, the angles always adds up exactly 180 degrees, while on a curved surface, the total becomes greater than 180 degrees. In hyperbolic geometry, however, the angle sum is less than 180 degrees. Second, the parallel lines also behave differently. In Euclidean geometry, there is only one parallel line through a point outside a given line, but in hyperbolic geometry, there can be infinitely many. According to James W. Anderson, parallel lines in hyperbolic geometry are more complex and can exist in multiple forms.
We discover that geometry depends on the assumption about the space and the parallel lines. When this assumption changes, the entire system of geometry changes. Mathematicians like Janusz Bolyai and Nikolai Lobachevsky shows that new geometries are just as valid as Euclidean geometry. This means geometry is not fixed, it evolves based on how we understand space.